The next property we need to talk about, while we're talking about trends in atomic size and ionic size, is something known as ionization energy. And this is actually the energy required to remove electrons from atoms. So the ionization energy is actually defined as the minimum energy required to remove an electron from the ground state of a gaseous atom or ion. And it's given the symbol I here. So to give an example of this, if we take sodium and we have it in its gas form and remove an electron from it to give the sodium ion and then that free electron, there's an energy value associated with that change. And we give this the symbol I1 because it's removing the first electron from sodium. And it has some energy value associated with it, plus 496 kilojoules per mole. And that leads us to a second kind of really important definition here, and that's that ionization energies, removing electrons from atoms or ions, are always positive values. We can think about the ionization process as simply promoting an electron to a really high energy level such that it's completely removed from the atom. So if we remember excited states from chapter 6, that was simply taking an electron and promoting it up to a higher energy level that's farther away from the nucleus. Well, if you keep doing that infinitely, then eventually that electron is simply by itself and is gone from the atom. But we know that increasing in energy level requires energy. Promoting an electron to a higher energy level requires energy, and thus ionization energies are always positive values. Now, we can have multiple ionization events. That's simply where we remove another electron after we've removed the first one. And those are given the symbols I1 or I2 for removing the second electron, or I3 or I4, etc. And the energy values associated with removing subsequent electrons are always higher than the energy for removing the first electron. So I2 is always higher in energy than I1, and etc. Let's look at a table that sort of describes some of this information. And there's a little bit more that we really need to pull out when we talk about removing electrons from atoms. And this whole process is for making cations. So cations and anions are involved in ionic compounds, but we talked about removing electrons from neutral atoms to form ions. Here now is sort of a measure of the energy associated with those processes. So if I look in this table, at the left we have a number of different elements, sodium down to argon, and then across the top we have various ionization energies, I1 all the way through I7, where each of these is removing a subsequent electron. So I1 is just removing the first electron, I5 is removing the fifth electron, I7 is removing the seventh electron. And what we'll notice is that there's sort of this stepped line as we go down. And at the difference between the value that's to the left of the stepped line and the value to the right of it is that there's a large energy difference between those two values. And it's larger than any of the energy differences between the previous values. So for example, if we take magnesium, the first ionization energy is plus 738 kilojoules per mole. And then removing the second electron after we've removed the first one requires 1451 kilojoules per mole. But if I go to remove the third electron, that requires not just an increase of about 1,000, but an increase all the way to 7,733 kilojoules per mole. The dramatic increase in the ionization energy. The reason for this dramatic increase is that the removal of the third electron from magnesium involves the removal of a core electron. So magnesium, if we draw out its electron configuration, it only has 2 valence electrons. So the first ionization energy will remove one of those valence electrons. The second ionization energy will remove the second valence electron. But then the third ionization energy is required. If you're going to ionize a third electron, that requires the loss of a core electron. And removing core electrons requires much more energy than removing valence electrons. They're closer to the nucleus for one reason. And so this large increase then illustrates where we've left off removing valence electrons and now have started removing core electrons. So if we take some random element, let's just take phosphorus, for example, it has 5 valence electrons. And so for the first 5 ionization energies, you'll see somewhat sequential increases in the energy, but not dramatic increases. It's only about maybe 1,000 kilojoules between each one, maybe 2,000 here at the end. Well, actually less than that, maybe about 1,300. But then that 6th ionization energy, after we've removed all 5 of the valence electrons, now we need to remove a core electron. That requires significantly more energy. So that's something important to keep in mind as we talk about ionization energies. There are also trends to ionization energies, simply similar to trends in atomic size. Here what we notice is that the ionization energy increases as we go left to right across the periodic table, and it decreases as we go down the periodic table. Now, what are the explanations for those? Well, the horizontal increase is due to the increase in the effective nuclear charge. If I simply compare nitrogen versus carbon, for example, the effective nuclear charge that those valence electrons feel in nitrogen is greater than it is in carbon, and thus those valence electrons are held more tightly, and so it's harder to remove a valence electron from nitrogen than it is from carbon. Now, the reason that we decrease as we go down the table, again, remember, we're increasing in energy level and thus distance from the nucleus at each time. And so those valence electrons, as they get farther and farther away from the nucleus, they feel the nucleus less and less. They're held less tightly, and thus it's easier to remove a valence electron from an orbital that's far away from the nucleus than it is to remove from one that's closer to the nucleus. And so it's much easier to ionize cesium than it is to ionize lithium, for example. There's one other trend that's very important to note in the periodic table here related to ionization energies, and that's that ionizing a filled subshell, so a filled orbital or filled set of orbitals like the s orbital or the filled set of p orbitals, is harder than from a partially filled subshell. So what this means, or illustrated here, is beryllium, for example, has a filled s orbital. It's 1s2, 2s2, so that its valence electrons are in a filled s orbital. Boron, however, that has one more valence electron, that extra valence electron is just in the set of p orbitals. The p orbitals aren't filled or even half filled, it's just in there. So it's actually easier to remove an electron from that partially filled p orbital set than it is to remove one from beryllium, where now you have to take it from a full orbital, from the s orbital. That subshell is filled. It's harder to take it from that than it is to take it from the then partially filled p orbital. And so that's why we notice that although there's a general increase left to right, boron is less than beryllium. And the same trend holds for gallium versus zinc. We have a filled S and a filled D, whereas now we just have, for gallium, we have just one extra electron. Its valence electron is just in the p orbital set all by itself. It's easier to remove that. And that's even true in some cases for even when we have 2 valence electrons. So it's still harder to ionize zinc than it is to ionize germanium, for example. But eventually, the increase in effective nuclear charge displaces that effect. There is also one thing to note here, in that although it's certainly harder to ionize from filled subshells than it is from partially filled subshells, sometimes it's harder to ionize from half-filled subshells than it is from just randomly filled subshells. So what do I mean there? Well, nitrogen has 3 electrons in the p orbitals. Following Hund's rule, we put 1 in each of those orbitals, and so all 3 of the orbitals in the p subshell have 1 electron in them. They're all half-filled. And that's actually stabilizing. Oxygen, however, has just 1 extra electron, so one of those orbitals now has a paired set of electrons. So the symmetry is now disrupted. And so it's actually easier to remove an electron from oxygen, even though it has a higher effective nuclear charge, than it is from nitrogen, because nitrogen has that half-filled subshell. And so you'll see that also between phosphorus and sulfur, and arsenic and selenium, although eventually as you get, eventually that effect diminishes as you go down the table. So that's just one other thing to keep in mind. What we will notice here as well is just notice the general trends going left to right, and remember the trends going down. Let's do a couple examples of this. So if we've got three generic elements, red, blue, and green, that are shown here, which of those indicated elements will have the highest first ionization energy, and which will have the lowest? And one thing I should point out real quickly is that these trends here hold for the second and third ionization energies as well, providing that we're not looking at removing a core electron. Of course, that then throws things off. So if we return to this problem here, which of these will have the highest first ionization energy? Well, I know that the ionization energy increases as I go left to right across the periodic table. So in the same row, green will have a higher ionization energy than red. Now I know that ionization energy decreases as I go down the table, so then the question might be between blue and red, which of those has a greater or lesser ionization energy? And what I could say is they're not in the same column. It's a little bit difficult to tell, but blue has a filled subshell. The s orbital is filled here, whereas red does not. So even though we're down one column, we're at the filled subshell, or down one in the column, we're in the filled subshell now. And so we would expect blue to have a higher ionization energy than red. And if we flip back briefly, we can see that that is true. So magnesium has a higher ionization energy than lithium, for example. So in terms of which of them overall has the highest ionization energy, well, the farthest to the right, that is, and the farthest up, that is the green. So green will have the highest first ionization energy. The lowest will be the farthest to the left, and the one that doesn't have, normally it would be the farthest to the left and the farthest down, but here the difference between farther left or farther down, the blue one has a filled subshell versus red not having a filled subshell. So red is the lowest ionization energy. Now the second question here is, which of these elements has the highest second ionization energy? And in this case, it might be a little bit unclear. First of all, let's just look at what happens when we go to remove these electrons. So if I look at my number of valence electrons, if I count my way across, green is going to have 1, 2, 3, 4, 5, 6. It will have 6 valence electrons. Blue will have 2, and red will just have 1. So if I talk about the second ionization energy, first I remove 1 valence electron, then I remove the next electron. Well, red only has 1 valence electron, which means that the second ionization is removing a core electron. For the other two, for blue, it has 2 valence electrons, so both ionizations are removing valence electrons, and for green, both ionizations are removing valence electrons. So the real difference here is core versus valence electrons. Removing a core electron is much higher in energy, so we would expect red to have the highest second ionization energy. So hopefully this is helpful in understanding how we kind of talk about valence ionizations of valence electrons and core electrons and the energies that are associated with those.